Continuing this week's talks, we'll talk a little bit about wind now. Basically, basics of wind. You're not going to get into a lot of heavy details maybe, but one of the things always to keep in mind is wind is a vector. What the heck is a vector? Well, it has both speed and direction. So where temperature is a temperature, you have one value. It doesn't move in different directions. Wind does. So the air motion is wind. So here's an ASOS temperature, ASOS package. It's what most airports have. Some use AWOS. Any major airport pretty much has ASOS at it. Notice this big long pole. At the very top of it, and this pole is actually 10 meters in height. So you're up there about 33 feet up. That is where the wind is measured with ASOS or at an airport. The wind isn't measured down here at the ground surface or whatever. It's measured 10 meters off the ground. So in a plane, a big plane or whatever, that's really not going to make a whole lot of difference to what you're feeling probably. But if you were a person walking by here, it could make a big difference in how the wind feels to you versus what ASOS is indicating. So one of the things that we talk about wind is a sustained wind. If you look at a METAR, and we'll do that here in a minute, you'll see a value for wind. We bring that right back up here. The wind is the very first element right after the time group. So right here is your wind. The first three digits indicate the direction of that wind. And that is the direction the wind is coming from. So if you put a compass right at that location and go out that line of compass for 100 degrees, you will see that's the wind. It's coming from the southeast. And the speed, sustained speed, is 5 knots. So these 2 digits represent speed. These 3 digits represent direction. So we now have wind vector quantity of speed and direction here. You can go all around here. If I want to look at another site, a little bit stronger winds, maybe not. But yeah, we got a little bit better here. You'll see the wind direction is 140, so it's southeast, 12 knots, and there's a gust. Oh, the gust is the highest speed that occurred within a 10-minute range of when this observation was taken. This observation was taken at 1755 Z. So around that time, 10 minutes before then, so from anywhere between 1745 to 1755, the wind peaked out at 19 knots. Not a long time frame, but it's enough to give you a value for gust. Now, if there's been a peak wind, highest wind over 25 knots in the last hour, it's going to show up down below there. So we know, because we don't see it here, there's no 25 knot wind going on at Huron today at this time. So that's how you read the wind in and out when you're looking at the METARs. So how the heck does wind get made? Well, wind comes, you can derive wind basically from the physics of wind, is Newton's laws of motion. And one of the first laws states, if there's some unbalanced force working on an object, it will undergo an acceleration until the force is balanced. So if you put the thrust on your engines in an aircraft, that aircraft is going to accelerate down the runway. Air parcels do it between the pressure gradient, puts a force on it, Coriolis force puts a force on it, and friction provides a force on it. So these 3 things are all contributing to the wind. Oh yeah, and another thing, air parcels move in 3 dimensions, not just 2. What you're always looking at on a surface weather map is 2 dimensions. But there's a third. That air parcel could be going upwards as well. So that's just something to keep in mind for the future. So we'll talk about pressure gradient. Let's go look at pressure gradient. Basically, it's the difference in pressure across a distance. So let's take a look at a surface weather map today. Where do you see the pressure isobars getting closer together? Well, I spot one right up here in southeastern Canada. Some of the stronger winds on this map are up here as well, 15 knots or so. So the pressure gradient right here is stronger than, say, down here in the southeast where there's high pressure. And then there's another line way over here. So you can see there's a long distance between lines. They get a little closer in the plains. So where they're real tightly packed together, that's where your strongest winds are going to be at the surface. So, and now that you've got the pressure gradient helping to push that air, remember, air is always going to want to flow from high pressure to low pressure. We're going to go that way. Now let's add the Coriolis force. The Coriolis force always acts to the right of the wind in the northern hemisphere. So if you go south in the southern hemisphere, it's going to be the opposite. But if you're in the northern hemisphere, the Coriolis force is going to act to the right. So this wind that started out going this way, away from this high pressure system, has been turned to the right, which would be towards the north. It's a southerly wind, but blowing towards the north because of that Coriolis effect. It's tending to turn that wind around. One of the things about Coriolis, basically, if you were an air parcel just above the ground here in Missouri, for example, in 1 hour's time, Missouri moved a certain distance, our Earth rotates. That same person stood at a location up here in Canada, the Earth isn't going to have rotated quite as far. Because let's face it, you're getting to the top of the world, there's no rotation, basically. Whereas at the equator, there's tremendous rotation. Well, the Coriolis force applies as that rotation gets less and less, the stronger the Coriolis force gets. So when you get to the top of the world, there's a very strong Coriolis force. When you get to the equator, the Coriolis force has gone to zero. So that's something else. Now we've got pressure gradient and Coriolis force working together. So where do we go from here? So we talked about the Coriolis force now. And Coriolis force acts over distance and time. So in other words, if you were to just move an air parcel very quickly a short distance, Coriolis force might not have much of an effect. Sometimes, for example, on a sea breeze, maybe the wind's coming in off the water. It may just keep moving directly from the ocean to the land at first. However, by afternoon, watch out, that wind's going to start turning to the right. So here on the East Coast where I live, that wind's going to be gradually become more and more southerly with time, that sea breeze. And that happens at Norfolk Airport, I know, a lot. And it probably happens in Florida as well, at the airports down there. So it's just something that's a fact with the Coriolis force working with the pressure gradient. Now, we talk about something called geostrophic balance. Well, when the pressure gradient force and the Coriolis force have worked it out that they're exactly opposite of each other, they're in balance. You really can see that when you look at a pressure map, aloft. So let's go aloft here to 850 millibars. 850 millibars, notice the contours here. So the tighter they are together, the stronger the wind's going to blow. But look how much together these are blowing, almost parallel. And this is only about 3,000 to 5,000 feet up. But say you wanted to go back here and look a little bit higher up, I can pick a map today at, let's go all the way up to 500 millibars or 15,000 feet up, and now you can really see they parallel the contours. There's a little tiny bit of turning maybe towards low pressure. You'll notice low pressure is going to generally be to the north and high pressure to the south, and that's typically what's going to be causing your pressure, the winds to flow here. The stronger and stronger we get into the winter season, instead of you seeing the pressure gradient up here in Canada that I'm seeing, your pressure gradient will be all over the United States. The whole area will be covered with wind, stronger wind than you're seeing right here. So let's go back here a minute with this, moving on to the next slide. And we'll say friction. Well, friction surface friction is roughness. So if the surface was really, really smooth, like a plate of glass, you would have very little friction as that wind moved across it. But we have topography out there. We have mountains that are going to slow the wind down. We have rough ground that's going to slow the wind down. So the wind is going to tend to slow, particularly over the rougher the terrain is. And so when you go over water, the terrain's not very rough, the wind's going to blow faster. If you ever watch the winds on the Chesapeake Bay, and I doubt you do, but I did for years, what you'll find is that the wind on the Chesapeake Bay is generally 5, maybe even 10 or 20 knots stronger than the wind over the land right adjacent to it. And that's all because of this friction and turbulence. Turbulence is just the air moving in all crazy directions is like turbulence. And you've all encountered it aloft. We're going to talk a lot more about turbulence later. And turbulence is something, if you ever looked in a coffee cup when you pour creamer in, and you'll all of a sudden just see you put a drop of creamer in, and that creamer just goes all over the place. It doesn't just stay in one little location. That's turbulence. That's the equivalent of trying to define turbulence. That's why the equations that meteorologists use to look at it are extremely complicated and not necessarily really good at figuring it out. So now you see those coming together. The final thing we talk about in this chapter is brought to you as the boundary layer. Or rather than just talk about it, we'll show you what it is really. And if you look at a sounding, all right, here's a temperature in red. We're just going to deal with temperature. This was taken last night at 0Z, or out here in Oklahoma City, which is what I'm looking at here, Norman. So this would be 7 o'clock, 6 o'clock Central Daylight Time 7 o'clock Central Daylight Time. So you can see here the temperature is going up pretty quickly. And you can see there's an elevation here. All of a sudden the winds are all southerly and then they turn to the west. That's the boundary layer. This layer where the temperature slows down its rate of descent, where it's not dropping as fast, is kind of the top level of the boundary layer. So the winds are going to be the atmosphere is really well mixed in this layer. The winds are generally, pretty close to uniform. In this case, about 20 knots or so out of the south, all through that layer. And once they get above that, you're getting above the friction layer of the atmosphere, and the winds are going to just start blowing more in terms of geostrophic wind without the influence of friction. So let's take a look at the same sounding, same location. And this will be 12Z today. Look at how shallow this inversion right here, where the temperature actually decreased with height, which occurs at night. And we learned that last week, this past module. That's where your boundary layer gets cut off at night, and you wind up with some pretty strong winds right near the surface here in that zone where the temperature decreased. But you wind up with a lot more mixed mash of winds aloft where the friction isn't playing. So let's look a little bit at a couple other things here I wanted to show you. One of the things we've been dealing with here today is with the pressures. If you look at a station model, let's see if we can find a really good one here. All right, let's use Oklahoma City, which is right here. We talked about upper left corner, 83 degrees is the temperature. Upper right corner is the station pressure. In this case, it's 1015.3 or 8. Can't really read it that well, but I'm not that interested in the tenths of millibars of mercury. But it's 1015.3. One of the things the Aviation Weather Center does, because it's dealing with pilots, it uses inches of mercury for the station, or the altimeter. It uses the altimeter. So, for example, here would be 29.99 inches of mercury, or 29.95 inches down here in Oklahoma City. So it's giving you the altimeter here, whereas most surface weather maps that you're going to see instead give you the station pressure. looking at 500 millibars too, here's the height. Instead of pressure, it gives you the height of that surface, and then in meters. So this is 500 millibars. It's 5910. So it's 5,910 meters up is that height of the 500 millibar surface here. Here's 5,750. So you can see if you looked across here, there's a pressure gradient right in there, a good one. This is higher, so the winds are, the atmosphere is sloping downward, so they're blowing that direction. They got turned to the right and wind up being parallel to the isobars. So it really holds true what they're showing you here. Can't go anywhere without at least looking at one satellite today. This is called the GeoCollar satellite. I'm going to loop it here to see if there's anything interesting we can talk about. And I know there is, for example, right now going on at my house. So I want to see if I can get a better view of it. And we'll do GeoCollar here. Here we go. There's a lot of showers developing near me. And you can actually see the tops growing with time right here. Notice early on there was like a big Q field, a little white area all around this area here was Q developing. What's happening here, look at where these are forming, right along the sea breeze. So you have a bay breeze out here, you have the thunderstorms forming there. Oh yeah, where are they forming out here? In the mountains. The mountains heat up, and then you wind up with a thunderstorm sometimes. So there's all kind of reasoning. There are very local processes today going on here. So it's just something to show you. I wanted to give you a little idea of it. And just looking at Doppler radar, let me bring you right back down to my house. And you can see there's the showers. This is a base reflectivity. So this is the reflectivity of the radar looking at the lowest elevation angle, which is a half a degree in the most recent one. But you can see I live about right here, just by the Chesapeake Bay, and James River flowing into the Chesapeake Bay. But there's a nice thunderstorm here on the sea breeze, several on the bay breeze fronts. So if you have any questions this week, please don't hesitate to give me an email or whatever, and we can talk about them. And I really hope to see some more discussions this week as well. I'll be putting out something about discussions here very shortly.